Hello everyone, welcome back. Today we'll be finding uh, electric field due to another charge distribution. Uh, just a second. Today our charge distribution will be circular arc, or you can say partial ring. Okay, so electric field due to, let's say, arc or partial ring. Okay, and electric potential as well. We'll be finding electric potential as well. Okay, so now if you consider an arc, okay, let's say this is arc of having charge q, right? You can also say it as a partial ring. Okay, suppose and we need to find electric field at this point, at the center. Okay, uh, another question we'll be doing, or another topic we'll be covering, where we need to find electric field at the axis of a charged ring. Okay, but here uh, we need to find at the center. Okay, at the center. So suppose this is a charge ring, okay, having charge q or linear charge density lambda. Okay, so and suppose if you join these two ends, okay, of the arc, let's say they make an angle theta between them. Okay, so if you divide this charge ring, okay, like this, in two equal parts, okay, consider a charge dq here. Okay, this dq, okay, is at an angle alpha from the vertical. Okay, from the vertical, and this dq is subtending an angle. This angle is actually d alpha. Okay, so what and the length of dq is what? It is dl. So relation between dl and dq will be, oh sorry, d alpha will be, dl is equals to r d alpha. Length of r is equal to radius into angle subtended. Now dq will be, it will be obviously lambda times dl, because lambda is what? Linear charge density. So you can write lambda, and dl can be written as r into d alpha. Okay, so uh, if you see that electric field due to this charge dq will be in this direction. Okay, and electric field due to charge, same charge dq, which is in opposite direction, it will be in this direction. So let's say it is d. Okay, and they make an angle alpha with vertical. Okay, so component here and here, what will the component, vertical component of electric field? It will be what? D cos alpha. Okay, and here it will be d sine alpha, right? So net electric field at the center will be what? This component will also be what? D sine alpha. Okay, so they will cancel out each other. These two will add to the electric field. Okay, so net electric field will be integration of dE cos alpha. Now this is a very important point, that what you will put the limits of integration. Okay, uh, if you consider only dE cos alpha, then you will put the limit from minus theta by 2 to plus theta by 2. Okay, and if you consider it 2d cos alpha, then you can easily put the limit from 0 to theta. Okay, we'll be considering it d cos alpha, and for your satisfaction you can do at your home as well. Okay, so limit will be minus theta by 2 to plus theta by 2. Okay, and we know d is what it is. I think you didn't know d. Actually, d is, I'm writing it here, dE is k dq by r square. Okay, and dq is what? Lambda into r into d alpha. So basically dE is k lambda into r into d alpha over r square. One r will cancel out, lambda into k into d alpha by r. Okay, now E will be, if you put d here, it will be k lambda into cos alpha, okay, d alpha, right, upon r, from minus theta by 2 to plus theta by 2. Okay, now if you integrate this, what will be the result? E is equal to k lambda by r. It will be sine alpha, and sine alpha from minus theta by 2 to plus theta by 2. Okay, so this will be, I think the result will be 2k lambda by r sine theta by. This will be the net electric field at the center of a charged arc, or you can say partial ring. Okay, and here theta is what? It is the whole angle subtended by the partial ring or arc. Okay, now if someone says that find net electric field at the center due to whole charging, okay, then theta will be what? Theta will become 2 pi. Okay, for semicircle theta will become pi. Okay, and you can put these values here and you will directly get the uh, net electric field. Okay, so net electric field at the center for charged ring will be what? Theta will be 2 pi. Okay, that means it will comes out to be 0. And for uh, you can say semicircular ring, okay, it will be theta will be pi, so answer will be 2k lambda by r. Okay, this is for full ring. Okay, and this is for semicircular ring. Okay, so in this way you can find the electric field. Now you need to find electric potential at the center as well. Okay, then again we'll be taking the same problem. Okay, here you have charged partial ring, or you can say arc. Okay, like this. Suppose they are subtending an angle theta. Okay, they have uh, linear charge as t lambda and radius r. Okay, and you need to find electric potential at this point. Okay, at the center of. So you know that dq will be what? Lambda times dl if we consider uh, a smaller elemental charge, okay, of length dl. Okay, so electric potential will be integration of dv, and d will be what? K dq over r. Means electric potential, let's say join this line. Okay, electric potential at the center due to this charge dq will be what? It will be k dq by r, since radius is constant throughout. Okay, now if you take this will be what? V, and k by r is common, it will be dq. Okay, and v is equals to k upon r, and sigma integration of dq will be what? It will be whole charge on the this you can say partial ring. Okay, if we consider whole charge on this partial ring, so k q by r. You can also write it as what? uh, what you can write? K, sorry, q can be written as lambda into r into theta. Okay, so v will also become k lambda into r. This is in terms of the charge, and sorry, just a second. The first one is in terms of the charge, and the second one is in terms of the linear charge density. This will be the electric potential at the center of a partial ring. Okay, or you can say arc. Thank you.